Welcome to chemistry classes by Vijay Kumar Sethi in class 11th chemistry unit 2 structure of atom. In this video we will discuss about dual behavior of matter and Heisenberg uncertainty principle. First come to the dual behavior of matter. The French physicist de Broglie in 1924 proposed that matter like radiation should also exhibit dual behavior, that is both particle and wave-like properties. This means that just as the photon has momentum as well as wavelength, electrons should also have momentum as well as wavelength. Wavelength is the characteristic of wave and momentum is the characteristic of particle, and both are related with each other by the de Broglie equation or de Broglie relationship, which is this: lambda is equal to h by mv, and this is equal to h by p, as this mass into velocity is equal to p. Mass m is the mass of particle, v is the velocity of particle, p is the momentum, and lambda is the wavelength of a particle. Then how can we prove that electron has wave nature? It can be proved by its diffraction pattern. Electron beam undergoes diffraction, a phenomena characteristic of waves, and diffraction pattern of electron wave is similar to the diffraction pattern of X-rays. At the same time, making of an electron microscope is based on the wave-like behavior of electrons, just as an ordinary microscope utilizes the wave nature of light. This electron microscope gives magnification of about 15 million times. Differences between electromagnetic waves and matter waves. These waves, that is electromagnetic waves, have electric and magnetic fields associated with them. Matter waves have no electric and magnetic fields associated with them. These waves can easily pass through the vacuum. These waves cannot pass through the vacuum. These waves travel with the same speed of light, that is 3 into 10 raised to the power 8 meter per second. Matter waves have different speeds. Wavelengths of these waves can be measured easily. Their wavelengths cannot be measured easily in case of matter waves. Electromagnetic waves are emitted from a source in space, while matter waves are associated with material particles. They do not exist without material particles. According to de Broglie, every object in motion has a wave character. The wavelengths associated with ordinary objects, that is macroscopic objects, are so short because of their large masses that their wave properties cannot be detected. This can be explained by taking this question. What will be the wavelength of a ball of mass 0.1 kilogram moving with the velocity of 10 meter per second? According to de Broglie equation, lambda is equal to h by mv, where h is Planck constant, m is the mass, v is the velocity. Put all these values in the formula and solve it. We will get this 6.626 into 10 to the power minus 34 meter. This is the wavelength which is associated with the ball, which is a macroscopic object, but this magnitude is very small. Clear? And also this is the one relationship between joule and basic units. 1 joule is equal to kilogram meter square second power minus 2. If we put this relationship in place of this joule, then we will get the unit of wavelength as meter. Next question. The mass of an electron is 9.1 into 10 raised to the power minus 31 kilogram. If its kinetic energy is 3.0 into 10 raised to the power minus 25 joule, calculate its wavelength. Use the formula kinetic energy is equal to half mv square. From this formula, first we will calculate the V. That is, V is equal to square root of 2 into kinetic energy divided by m. Put the values. Kinetic energy is given and mass is also given. We solve it, then we will get 812 meter per second. Then by using this velocity, we will find out the lambda, which is equal to h by mv. Put the value of h, m and v. If we solve it, then we will get this 896.7 nanometer. Okay. Next question. Calculate the mass of a photon with wavelength 3.6 angstrom. In this case, wavelength is given in angstrom. Convert this angstrom into the meter by multiplying 10 raised to the power minus 10. Velocity of photon means velocity of light. Apply the formula, that is this, lambda is equal to h by mc. Okay. From this we have to find out this m. We can say m is equal to h by c lambda. Put the values. This is h, this is c. C is the speed of light. And this is lambda is given. And if we solve it, we will come to 6.135 into 10 raised to the power minus 33 kilogram. Heisenberg uncertainty principle. First, its statement. It is impossible to determine simultaneously the exact position and exact momentum of an electron, or we can say exact position and exact velocity of an electron. Mathematically, this can be expressed like this. Delta x into delta p is equal or greater than. This indicated equal or greater than h by 4 pi. And as we know, this momentum is m into v. Okay, that's why we can find out, or we can get this formula. Delta x into delta v is equal or greater than h by 4 pi m, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, delta v is the uncertainty in velocity, and m is the mass of particle. From this relationship, we can say the minimum product of uncertainty in position and momentum is equal to h by 4 pi. Okay, and same conclusion we can find out from this. That is, the minimum product of delta x and delta v is equal to h by 4 pi m. If the position of the electron is known with high degree of accuracy, it means delta x is small, then the velocity of the electron will be uncertain, that is delta v is large. On the other hand, if the velocity of the electron is known precisely, that is delta v is small, then the position of the electron will be uncertain, that is delta x will be large. Now, we will take one example to understand the uncertainty principle. Suppose you are asked to measure the thickness of a sheet of paper with an unmarked meter stick. That is, that scale is not there on meter stick. Obviously, the results obtained would be extremely inaccurate and meaningless. In order to obtain any accuracy, you should use an instrument graduated in units smaller than the thickness of a sheet of the paper. Similarly, in order to determine the position of an electron, you must use light or electromagnetic radiation. The light used must have a wavelength smaller than the dimensions of an electron. The smaller wavelength photon have high momentum. See this sentence. Smaller wavelength photon have high momentum. This can be seen from this relationship. Lambda is equal to h by p. If this is smaller, it means this will be large. If wavelength is smaller, momentum will be high. And high momentum photon of such light would change the energy of electrons by collisions. In this way, we would know very little about the velocity of the electron after the collision. You can see from this diagram. This is the before collision. A photon strikes an electron during an attempt to observe the electron's position. Okay, this indicating the photon. This is moving electron, and after striking, what happens? Okay, we can say this electron velocity change. After collision, the impact changes the electron's velocity, making it uncertain. Clear or not? That is, when this shorter wavelength of photon or photon of the shorter wavelength strike to this electron, then after the collision, its velocity will be uncertain due to high momentum of the striking photon. You can also see from this diagram, a high frequency means shorter wavelength. Photon gives a more accurate measurement of position. We already discussed, to get the position, we have to use the short wavelength. When wavelength is short, its frequency will be high. High frequency means high energy. Okay, and it causes a great uncertainty in momentum or velocity. Again, you can say this is the incident photon. Okay, and you can say this to this wavelength is short wavelength. Short wavelength means high frequency. High frequency means high energy. Okay, then after the collision, its momentum will be uncertain or its velocity will also uncertain. But if you use this like this, low delta x, if this wavelength is short, then uncertainty in position is low, but uncertainty in momentum is high. On the other hand, if we use the photon of higher wavelength, see from this indicate the wavelength, higher wavelength. It is when wavelength is high, then we can say uncertainty in position is high, but uncertainty in momentum is low. Is it clear? It means if we find out the position of electron with the less uncertainty in position, then there will be the larger uncertainty in momentum. Clear? Either this will be higher, then this will be low. If this is higher, then this will be low. And the product of these two is always equal or greater than h by 4 pi. Or we can say minimum product is equal to h by 4 pi. Significance of uncertainty principle. It rules out existence of definite paths or trajectories of electrons and other similar particles. Now, what is the meaning of this path or trajectories? The trajectory of an object is determined by its location and velocity at various moments. Second one is the effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. Again, it can be explained using this one problem. If uncertainty principle is applied to an object of mass 1 milligram, 1 milligram means 10 to the power minus 6 kilogram, then the product of the uncertainty in velocity and position, we can find out this. This is h by 4 pi m. Put the values. H is Planck constant. This is 4, pi is 3.14, m is 10 to the power minus 6 kilogram, and this will nearly 10 to the power minus 28 meter minus 2 second minus 1. The value of delta V multiplied by delta X obtained is extremely small and is insignificant. Okay, that's why we can say Heisenberg uncertainty principle is insignificant for macroscopic objects. But if same principle is applied for an electron whose mass is 9.11 into 10 to the power minus 31 kilogram, again we can find out delta V multiplied by delta X for electron, then this will come to 10 raised to the power minus 4 meter minus 2 second minus 1. And if exact location of the electron is to an uncertainty of only 10 to the power minus 10 meter. If uncertainty of electron in position is 10 to the power minus 8 meter, then we can find out the uncertainty in velocity, and this will be nearly 10 to the power 4 meter per second, which is so large that the classical picture of electrons moving in Bohr's orbits, that is fixed orbits, cannot hold good. See one more question. A microscope using suitable photon is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? First, we use this mathematical expression for Heisenberg uncertainty principle. Delta X multiplied by delta P is equal to H by 4 pi, and this delta P is replaced by M delta V. Then from this we can find out delta V is equal to H by 4 pi delta X M. Put the values. This is Planck constant, this is 4, this is the value of pi, and this is the uncertainty in position which is given, that is 0.1 into 10 to the power minus 10 meter, and this is the mass of electron. Then we can find out this will be equal to 5.79 into 10 to the power 6 meter per second. See one more example. A golf ball has a mass of 40 gram and a speed of 45 meter per second. If the speed can be measured within accuracy of 2%, calculate the uncertainty in position. So first, that is accuracy of speed is 2%. It means uncertainty in the speed is 2%, and speed is 45 meter per second. That's why 45 into 2 by 100, this is equal to 0.9 meter per second. This is the uncertainty in speed. Okay, and this mass is given in gram. Convert this into kilogram. Then use the Heisenberg uncertainty principle. Delta X we have to find out. This is equal to H by 4 pi M delta V. Put the value. This is H, this is 4, this is the value of pi, this is M in kilogram, and this is delta V, and this will be equal to 1.46 into 10 to the power minus 33 meter. This is very small. Okay, that's why for such type of objects which can be seen by our naked eyes, this uncertainty principle is not significant. We have discussed some shortcomings of Bohr model. Now what are the reasons for the failure of the Bohr model? It did not consider the wave character of electron, that is ignores dual behavior of matter, and it contradicts Heisenberg uncertainty principle. Bohr model says that electron revolve in a definite circular path, but according to Heisenberg uncertainty principle, we can't predict the exact path. Is that clear? These are the some failure of this Bohr model. Thank you.